Hello and welcome to the first of the asynchronous weeks for CSCI 5100. This will be a lecture on diagonalization. To put things in just a little bit of context, right, we are following up from earlier coursework, setting up the acceptance and emptiness criteria for finite automata or regular expressions for context-free grammars or pushdown automata, and we have now demonstrated that we need some more powerful proof technique in order to answer the decidability, which is a Turing machine that accepts or rejects, and recognizability, which is a Turing machine that either accepts or does not, so it may never halt. And we're going to use diagonalization to show this. So this week, we're going to introduce the notion of diagonalization. This is also often called contours diagonalization. We'll proceed through this, and then we'll be in a position to determine undecidability next week. Okay, so what's the sketch of what we're doing? We're going to do a few things. We're going to do diagonalization, and fun fact, we're going to do nothing else. That's all we've got for now. That will be more than enough to do for one video lecture. So let's motivate this. We want to answer this question. Can we prove or disprove this? If this is our theorem, what do we want to do? So let's go through each of the steps. This is logical negation, and this is decidable, which I've written as a predicate. So it is not decidable to have the following language. This is the acceptance language for underscore Turing machines. And what is the acceptance language for Turing machines? Well, this is a language that would be accepted by a Turing machine, but is also about Turing machines. We take a set. Why is that? Because this is a language, and languages are sets of strings. Often we say bit strings, right? So they're sets of sequences of sigmas, where sigmas are the alphabet, right? Or elements of sigma, perhaps. We take these brackets here, which these represent the string encoding of some information. Why is that? A is a set of strings. So set of strings, logical negation of a predicate function that accepts a set of strings and returns true or false, right? Okay, so then this is the set of strings. This is a string. This is an element of the set of strings. The first element is M. M is a Turing machine, right? Turing machines do what? They accept, reject, or potentially do not halt on some input. What is the input? W. W is a word. So if the word, so if this string is an element of the language accepted by this Turing machine, we perhaps should say L of M here, right? I think it makes no difference, right? So this is the string representation of a Turing machine. This is the string representation of some string. So this is a string, and this is a string. This is a Turing machine. And then we will have some Turing machine that accepts this language. Okay. Logical negation. Predicate function over sets of strings. Set of strings. String. Turing machine. String. So how are we going to show that this is either true or false, right? At this point in time, we just want to know which it is. We will find out that it is false, right? But we don't need to make such strong claims at this time. We are going to introduce the terminology undecidability for this. Undecidability is it's a famous and important problem, and it's a famous and important way of describing things. I always think of the impossibility of distributed consensus, right? That's what I always think of. But, there's other things that are undecidable. Is there, a prime number over a certain size, or between, two impossibly large values, something like that, right? And in order to answer this question, we're going to use diagonalization. And diagonalization is coming over from number theory. I solved a number theoretic problem, and we're going to use it to solve that same number theoretic problem. So we know what diagonalization is, and then once we know what diagonalization is, we can proceed from there. Okay. I claim it's the only known technique to show undecidability. That probably depends on what you mean by known technique. They sort of reduce to each other, right? So I think of this as the only meaningful technique, perhaps. And then once we have one undecidable problem, then we can do reductions to it. But we're going to begin with diagonalization to show the first undecidable. Okay, so we're going to ask a question about the size of infinity, right? And so I gave the example earlier of prime numbers. So if you take any infinite-sized, I don't know, subset of the integers, they're the natural numbers, right? Very hard to answer if there's prime numbers or not in that. I guess some of them are quite easy, right? If it's multiples of 2 that are greater than 2, you know that, but you don't always know things of this nature, right? So there are different infinite sets, and we're going to look at them and we're going to examine them. We're going to examine them mathematically. So let's introduce a little bit of set theory. Everybody loves set theory, so we're going to introduce a bit of it here. Numbers and sets are closely related, right? You can construct the reals from sets. My first diagonalization I would have done in probably spring of 2012 in an undergraduate calculus class where we would have constructed the reals using sets, I think. And so that was a entry-level college mathematics class in a theoretical mathematics program. So that's about where this comes in. Mostly of use for theory, but of course the practical implications of being able to demonstrate a computer cannot necessarily return in a finite time from being asked certain questions is immediately applicable, especially to web servers and real-time computing. The microcontrollers that run cars. At Lagrange University, of course, Lagrange's position in the regional and national, and I guess you could even argue international economy, right, is so close to the major Kia plant, right? Everyone over there at Kia has to make sure their microcontrollers always halt, right? So they have to do certain technical considerations. They have to have certain assessments about memory safety, right? And then they also have to have certain theoretical conceptions that they can never ask a microcontroller chip in a car on some safety critical or real-time critical feature to solve a problem that is undecidable, right? They must know they're not doing that. There has to be some form of assurance. Often in practice, these assurances are formed with heuristics and tests, but we can make theoretically sound claims, right? So I think that's George Cantor. I think I spelled that correctly, and I think that's how you say the name. 1891, long time ago. The reals have been around much longer than Turing machines, right? We had Turing machines in 36, 37. So by the time they came around, that was 45 years after Cantor's diagonalization proof. Cantor had previously determined that there were two sizes of infinity over the same studied sets. I think many years before this, perhaps 2 decades before this, right? To my knowledge, I've only ever seen diagonalizations. Diagonalization is the enduring proof technique, and I think in that sense it is the enduring proof technique in the same way that the Turing machine is the enduring proof technique, even though Gödel's general recursive functions and Alonzo Church's lambda calculus predate it. Oop, I clicked out of my screen here, right? And just so you know what's coming up, right? What we're specifically going to do is we're going to show that even though there's an infinite number of natural numbers and an infinite number of real numbers, there are more real numbers than natural numbers. That's a larger infinity. And we're going to have to make some assumptions to show this, right? But these are useful and important assumptions. The importance of diagonalization is not exclusive just to, I guess we can say, the field of computer science, right? This is over automata theory, so it's quite close to mathematics. It was also used by Kurt Gödel in his incompleteness theorems to show that, all systems have central axioms which cannot be proven. So this informed us that we must make some assumptions about any mathematical proof system which we use. We're actually going to discuss a little bit some of those systems today, and one of them, for example, is the continuum hypothesis that's sort of swirling around here. It depends on what you mean by numbers, whether there is something in size between n and r. And so this diagonalization has come up, and it's important for a variety of reasons, and it has been necessary for the advancement of human understanding into mathematics and computer science, right? And then I'm not going to attempt to say this thing. Entscheidungsproblem problem. This is, I guess, German. Um, and we call those in English, often we call them decision problems. Why do we call them decision problems? Well, a Turing machine either accepts or rejects some input. We can argue that that is deciding yes or no or returning true or false, right? So a Turing machine decides something. And from this, we have gotten to the notion of between decidability, where you get a yes no back, or recognizability, where a Turing machine may accept something. So the category of problems for which we study with Turing machines is decision problems. Here's an example of something that's not a decision problem: addition. Addition takes two numerical values and returns a new numerical value, does not return a yes no value. Here's an example of the decision problem variant of addition. You take three numbers and you see if the third one is the sum of the first two, right? So that is sort of the different way we formulate decision versus recognition versus computation versus calculation. So let's take some functions. Why are we going to use functions, right? Well, I think when Contour was hanging out trying to figure out this problem, the thought is, well, how do we even compare n and r? And the answer is when you're comparing two sets, you often write a function between the two of them, right? So we're going to take we're going to construct, functions over essentially the natural numbers. We may construct them over other things, and one of the things we can do, for example, is we can show that, given the natural numbers, we can write a function that is, not that different from the formulation of how we would write a function that describes some infinite language, right? Um, and that function can perhaps produce the integers, or perhaps can produce the odd integers, right? Or can produce the negative integers or anything else, or perhaps it produces the natural numbers modulo something, right? And that would not be a bijection then. Okay, so what we're going to claim here, and this is our central axiom that cannot be proven, right, under Gödel incompleteness. We're going to claim that given two sets of infinite size, the way to tell if they have the same or different infinite size is we're going to write a function that is 1 to 1 and on to. And we're going to define these terms extremely rigorously before we go any further, because if we don't define them rigorously, what are we even doing, right? So we're going to introduce some notation. I am going to use this notation, which is a script lowercase f followed by a colon, followed by usually an uppercase sort of mathematical script Latin character, so something in the alphabet. That's going to denote a set. Then we're going to use a right arrow, and we're going to follow that with another set, which is the uppercase italicized Latin character. This is all formulated in LaTeX, and it's formulated in LaTeX uncomplicatedly. You can look at the source code. Something important to keep in mind about these functions, right, is I have a right arrow there. Maybe that right arrow to you doesn't feel like something that exists in the notion of set theory. That's just fine. You can also think of this as a set of ordered pairs, and of course you can construct ordered pairs out of unordered sets as well. The real reason to use this arrow is we're talking about different things. We've used this previously, right? On the deterministic finite automata, we had a state of the finite automata and a letter of the input alphabet. And we took a cross product of those. We said we had a pair of those, and then we drew an arrow to represent a new state. Well, all of those things are just nested order pairs, right? But they have different meaning to us as human theorists. And so we use the arrow to denote this different meaning. And it remains mathematically rigorous because they are simply sets of ordered pairs. And an ordered pair is a set of sets, right? And we can construct it from sets. So we're going to introduce now injectivity using the notation that we have previously. Injectivity is the first of the two features that we require our function to have to establish comparative sizes of infinity, and it is also called a one-to-one function. I'm going to, generally speaking, try and stay away from this term, one-to-one. for a variety of reasons that we'll see in a minute. So I'm going to really specifically try and use the term injective. To me, the term injective has the benefit of being a domain-specific and a technical term. And I think one-to-one can feel quite ambiguous quite quickly because those are two non-technical terms, one repeated twice, joined by a preposition, or in this case, an inposition, I guess. So I strongly prefer the term injective, and I recommend the uses of injective in your own language, in your own thinking. So what is an injective function? Well, it maps distinct elements of its domain, or the elements of the domain. That is the first set at the beginning of our arrow, perhaps the set of inputs, right? And it's going to map using these ordered pairs. So there will be an order pair that contains elements of the first set in its first position, and it's going to map them onto distinct elements of the codomain. So what does that mean? We have the codomain, or perhaps the set of destination. These are elements of the set B. And if I have some element of set A, we'll say lowercase a is taken by the function, or perhaps in a pair with some element in the function. And that lowercase a corresponds to perhaps a lowercase b. And then we say that for each one of these ordered pairs, they are distinct. So no two elements of the initial state or set of inputs A correspond to the same element in B under the function. Here I've written that out mathematically. For all x1 and x2, if x1 does not equal x2, then f of x1 does not equal f of x2. I hope that's clear, and I hope that feels relatively simple. Here is a visual representation, and of course you can also look at the source code. This is a graphviz dot graphic. Hopefully that is visibly accessible to you. What we have here is we have the set A, which contains 1, 2, 3, and we have the set B, which contains W, X, Y, and Z. So this is a mapping from natural numbers, or perhaps natural numbers set minus 0 and no larger than 3. And we map it to a subset of the lowercase Latin characters. We note that 1, 2, and 3 all map to distinct elements of B, and we notice we are under no obligation to map to every element of B, right? So Y has no pre-image, perhaps. There is no element of A that maps to Y. And so this is a visualization of an injection. This example is taken from Wikipedia, which is the same source as that prior block quote. And then I generated it myself in GraphViz, so you can see how to generate these yourself. Injectivity is also specified in this manner. Every element of the function's domain, which is the set of destination. This is B, this is W, X, Y, Z. So the set of, the set for which is receiving the function, perhaps, is the image. What does image mean? Well, the image of a value in sort of the set of inputs is the single value, singular value, individual value. Right? And now let's be very careful here about what's going on. Every element, this is essentially a for all, is the image, which means image is a term with respect to an element or a specific value. Perhaps this should say element instead of value, right? Or the single element. I'm using values here, of course, right? But they could be things other than values. This could, for example, be a bijection between sets of functions, in which case we would probably want to say element instead of value. So if you are in the set of destination, if you are one of those elements, if you're W, X, Y, Z, you at most are f of x for one specific x. The set of inputs and the set of outputs do not have the case such that one of the elements of the set of the outputs has two elements of the set of inputs for which it is the output. Let's look at an example. F of x equals x squared from the naturals to the naturals. You can, of course, apply this to the reals or any other number as well, right? So 1 maps to 1, 2 maps to 4, 3 maps to 9. We note that each of the elements to which this function maps is unique. Every natural number has a unique square. And then we also note, importantly, that not every element of the naturals is mapped to from this function. 3 is not a perfect square, 5 is not a perfect square, right? So there are elements of the naturals that are not elements of the set of the destination. That is fine. We are under no obligation to map to every element of the naturals. We are simply under obligation to map from the naturals to unique elements of the naturals, and so we do that. And what this establishes is that, for example, even though not every natural number is a perfect square, there are the same number of perfect squares that are in the natural numbers as there are numbers that are either perfect squares or not perfect squares within the natural numbers. And so this is an interesting argument, or this is an interesting feature that arrives from the claim. There's the same number of even numbers as there are all numbers. It's the same number of, and so on. Right? We can also do this with x cubed over r to r, right? What else do we have? Python ORD is an interesting example, right? So ORD takes a printing character such as A, and we would include that A in single quotes. It could also be the exclamation point or the bang character closed in single quotes. It could be the ampersand. It could be a numerical value like 8. Each of these is printing characters. They are printing characters in the Unicode character set, and each one of them has some corresponding numerical value. I believe they're all in the range of 0 to the 32, but I don't know. Many of them, all of the ASCII ones, are in the range of 0 to 127. So here's an example of a function that is not simply over numbers. It is over printable characters, which is a finite set, and the natural numbers, which is an infinite set, but it is also over, I believed, the unsigned integers of up to 32 bits inside. So we have UTF-8 or UTF-16 or UTF-32 or something of this nature. And so that is a mapping to a finite subset of the natural numbers, and specifically the natural number set including 0 in this case, if we do need to specify that. Here's an example. I've just printed out every fifth one of these things. I just mashed my keyboard for a moment. You can see that that is the Latin characters, lowercase in alphabetical order, followed by all of the shift characters that are represented by shift numerical code on a US English keyboard. And we see that each one of these maps to some numerical value. So ORD is injective. In public life and civic life, somehow people get social security numbers. I believe you get one if you are born in the United States, and you might get one when you become a citizen or something of this nature. And they're commonly used for authentication. So when I was applying for a job at Lagrange University, I provided them with documentation that I had a United States social security number, right? And so the set of social security numbers are some number of digit integers. They're natural numbers because they're unsigned. So some subset of the natural numbers, right? And humans in the United States, I guess, with a social security number, right? Because not every human in the United States has a social security number, importantly. That is injective because no two humans map to the same social security number, right? No one has the same social security number. That's why they can be used for authentication, right? Let's look at some non-examples. We can look at the negation of examples, and we've sort of already introduced an example there. If we look at humans in the United States instead of, for example, people with social security numbers in the United States, which is of course defined by construction, then there exist many humans that have no mapping. X squared from R to R. There is no way to generate negative numbers with X squared. So this, matters in some way. And since we can generate no negative numbers with X squared, we simply take -1 and +1. When we take -1 and +1, they both map to +1. So that means that the preimage of +1 under the function x squared is a set containing 2 elements. So there's not a singular. So this is not 1-to-1 function in that sense. It is now a 2-to-1 function. And it is 2-to-1 function along all of R positive, right? Um, Similarly, we can take various operations. I just wanted to do something from the natural numbers to the integers, right? And here's one example. Um, Emails to humans, right? Um, there exist multiple emails that map to me, Calvin Deutschbein, as a human. I have my official academic.edu email, and then I have a personal professional email that is hosted by the commercial entity Gmail, which is owned by Google, which is owned by Alphabet. Surjectivity is the other thing. Wait, close, stop, pause. That's the end of injectivity. Injectivity is also called one-to-one functions. That is one of the two things that we have to have. Just putting this all together. We have to have a function which is injective, but it must also be one other thing. That one other thing it has to be is surjective. Right, so we're going to take surjectivity. Okay. We're going to term a function to be surjective under the following conditions. For every element y of the function's codomain, or as we have termed it, the set of destination, there exists at least one element x in the function's domain, such that f of x equals y. So what does this mean? If I am mapping onto some set, and this is why it is called onto, I must be able to map to every single value or element within that set. For all y in the set of destination, there exists some x, which in the set of inputs, such that y equals f of x. That's all it means. Here's a visual example. We can take our set of inputs, A, to be 1, 2, 3, 4 numerical values, and we can take our set B to be W, X, Y, alphabetical characters that are lowercase within the Latin character set. And we can say we map 1 to W, we map 2 to X, and then we map 3 and 4 to Y. What this means is that every single element of B has some corresponding pre-image or something within A which maps to it, right? There are no elements of B that do not have some incoming edge from A. Let's look at the properties of surjectivity. Every element of the function's codomain. What is a codomain? It's the set of destination. It is the set B if the function is f of type A arrow B. And we say that it is the image. We have introduced image previously. Image takes elements over the set of inputs. And I want to say basically that the codomain is the image. Stop. Codomain is a set. Let's go back. Image refers to elements. For every element, image. So this is a different meaning. The image of a set and not an element is distinct. The image of A under F is the set f of x, the elements of B, for all x that are elements of A. Let's look at some examples. Absolute value. We can reach every natural number by applying absolute value over the integers. Right? We can take natural log. This maps to all real numbers, right? We asymptotically approach negative infinity as we take the natural log of values that approach 0 from the positive direction, and then we asymptotically approach positive infinity as we asymptotically approach positive infinity in the set of both inputs and destination. We can just invert ORD, right? We can do chur. Takes a finite subset of infinite numerical values. Python does have at least theoretically infinite numerical values, right? And with ORD, you can map to every single printing character. And we have to argue a little bit by definition. Oh, of the printing characters for which Python recognizes. Sure. So we define the set of printing characters that Python recognizes, and we say, yes, we can map into that thing. We can see some interesting things to which we may map. I don't really know what any of these are, but, they're fun. Names are suggestions. So I've met other people named Calvin, right? Met other people named Deutschbein. I've met other people who are professors. And so, to my knowledge, there could be special cases. Every person has a name, but these names are not unique. There are other Calvins, there are other Deutschbeins, there are other professors, right? X squared is a bad example here because we cannot get to -1. 2 of x is a bad example here because there's no way we can get to 3, and 3 is a natural number. Right? English words to Latin character spellings. I can spell that word, but it's not a word, right? And with that, we have defined one-to-one functions and on-to functions. And now we are going to put those two things together, and we're going to create something called a bijection. Bijection is an extremely useful term to have access to. So we appreciate this term because it's a useful way to describe things. So we begin. A function is bijective if it is surjective and injective. I transposed the order. If it is injective and surjective, it matters not which order you say these things in, right? A bijection is one-to-one and onto. For all x1 and x2. If x1 does not equal x2, f of x1 does not equal f of x2. Injective. And it is surjective. For all y in the set of destination, there exists at x in the set of inputs such that y is equal to f of x. Another way to say this, and this is perhaps a way to think about it, so I like to think of functions as sets of ordered pairs. And so then I think of the injective functions as a set of sets of ordered pairs. And the surjective functions I think of similarly. So to me, these are all sets of sets, right? Which is a natural thing to have sets of. And so if I take my two sets of sets and I take the intersection of the injective and surjective sets, then I get the bijective sets. This is an example of a bijection. Every element in A corresponds to exactly one element in B. Every element in B corresponds exactly to one element in A. I would have here, for example, had the liberty to make those arrows go both directions because the function w to 1, x to 2, y to 3, z to 4 is also a bijection. This is a bijection in both directions. Could argue, in fact, that we no longer need our pairs to be ordered. Right? Then we would have some confusion about which direction our bijection is flowing, but it makes no difference. Here is the summary slide. So let's take a look at this. Let me move my mouse. What do we have going on here? I very much think of this in terms of a grid. Above this line, we have injective functions. And on the left-hand side of the screen, we have surjective functions. Bijections are injective and surjective. And we also exist functions that are neither. So there are 2 elements that correspond to z and 0 elements that correspond to y. So this is neither injective or surjective. So we have an I over here and an S over here, and then set. There's various ways to label this. I took some of the labels off of this grid because these visuals were getting too small. Okay, our terms. I have never, I think, in my life said the term bijective function. I know they're functions. It's just, to me, I think of them as bijections. And this notion that they don't have to contain ordered pairs, because a bijection can go in either direction, is like relatively important to me just cognitively. I don't know that it matters theoretically. I don't know that it matters practically or formally. But I do just think of them as bijections. I think of them as this special thing that's not quite like the other functions. And they are kind of a special thing. Like this is very novel, this exact correspondence between two sets. You could even go as far as to argue it means that the sets are equivalent, right? The thing that makes the even natural numbers different from the non-even natural numbers is actually how we apply operations over them. But those operations are not part of the natural numbers, right? We can simply define them differently. So anything for which there exists a bijection means that in some ways those just are the same things, right? A very, very interesting idea. Here is why I don't say one-to-one. I have often seen bijections referred to as one-to-one correspondences, and then you say, hey, what's a one-to-one correspondence? Someone says the very confusing statement. So this is a confusing thing to say, so be cautious while you think about it. A one-to-one correspondence is both one-to-one and onto. You say that's a recursive definition, and it's not, because a one-to-one correspondence is a one-to-one function and an onto function. And one-to-one means different things when it's referring to functions and whatever a correspondence is, right? And the correspondence, of course, is where the pairs are unordered. Um, to me, that seems bordering on deliberately confusing, and it seems confusing in the same way. I have a profound distaste for referring to both the images of elements and the images of sets, but we do need some way to describe these things, and there are historical terms that are used. What this means is that I say bijection, injection, and surjection, and I do not say one-to-one if I can help it at all. I only mention one-to-one because I'm, concerned that if you go on Stack Overflow or Wikipedia or read a textbook, you're going to see the term one-to-one floating around, and it's going to mean two different things. There are one-to-one functions. There are one-to-one correspondences and relations. They're distinct. Let's look at some examples of bijections. Okay. The identity bijections, that's the most obvious one. Identity is always a bijection onto itself, right? Just so happens that x cubed maps from R to R, right? That's fun. Also works for n to the integers. And how do we do that? Well, what do? I take the integers, I divide them by 2, essentially. That's what's going on here, right? We divide by 2. And we also take modulo. And that's integer division by 2, right? So this maps onto the integer. So what's this going to do? This is essentially going to create 2 of every integer, right? Then we take the value modulo 2, and we multiply that by 2. And we subtract 1 from it. So if this thing is an even number, this thing is 0, this thing is 0, and this thing is negative 1. If this thing is 1, then this thing is 1, then this thing is 2, then this thing is 1. So what is this? This is a toggle. This toggles from positive 1 to negative 1. And it toggles every single time we increment, and this increases every other time we increment. So we take 0, we take 2, or well, we take 1, right? We take 1, 1, integer division 2 is 0, doesn't matter what this thing is. We take 2, 2, integer division 2 is 1, 2 mod 2 is 0, this is 0, this is negative 1, so we take 1 times negative 1, get a negative 1. 0, let's see, 1, 2, we take 3. 3, integer division 2 is 1. 3% 2 is 1. 3% 2 times 2 is 2. 2 minus 1 is 1. So we take 2, no. Yes, we take 1 because 3% 2 is 1. We take 1 times 1 and we get 1, and so on. So this here is the integers constructed from the naturals. Are we cheating? Of course we are. We should be slightly annoyed here that every natural number is an element of the integers, right? Which means that n is a subset of the integers. Not necessarily strict, we haven't established strict here, right? And we also notice that there exists x element of z, such that x is not element of n, we take negative 1, for example. So that means n is a strict subset of z. And there also exists a bijection from n to z, which means they're the same size. So the cardinality of n and z is the same, even though there are elements of z that are not elements of n, and there are no elements of n that are not elements of z. That's kind of weird. It's not really cheating, it's just weird. It means the size of infinity are non-intuitive, right? I can add even potentially an infinite number of elements to a set without increasing its size. And this gets into the notion of countability. The naturals, the integers, and q, which are the rational numbers, the fractionals, those are all the same size. I was surprised too, right? There's in fact infinitely many rationals for every natural, and it doesn't matter at all. We call these countably infinite because we can count them. What does counting mean? Counting means there's a bijection to the naturals. That's just what that means. It's sort of, we term them, right? It's by definition we say countably infinite rather than there exists a bijection to the natural number. To me, like intuitively, I think in my mind, these are all simply the natural numbers, which means I can express them in binary representations in computer memory, right? For example, we simply express them in different ways. Pythonic count is the countably infinite iter tool. There are other iter tools, of course. Q it is non-trivial to show the bijection to Q. I could write out the Python expression, right? It's relatively painful and it's difficult to convince yourself it's correct because you're dealing with infinities, right? We're going to show something that's very close to a closed form, just to show an example of how we do these things. Okay, so how are we going to do this, right? Well, all right, let's take Q. And the first thing we're going to do is we're going to cheat. We're going to say we're only going to look at positive Q. Why can we do that? Well, we already showed that if I get the positive version of something, I can construct the negatives from it fairly quickly. So why bother? So I'm only going to look at m over m, for which m and n are both elements of the natural numbers. And this is going to save me a bit of a headache. It avoids double counting, right? So if I do this with the integers, I'm going to have negative m over negative n, which corresponds to positive m over positive n. No one really wants to do that, right? So we're just going to do the positive rationals, and we have already demonstrated we can go from the positive rationals to all rationals. We are going to make a table. I love tables. One of the great things about tables is if you have an n table, a table of size n by m, and n and m are finite, then that means the table size is finite. That's pretty useful. And separately, we're going to claim that if we take a table that is of size n, by which I mean big N, so if I have the countably infinite number of rows and countably infinite number of columns, well, that ought to be countably infinite as well, right? Because I can keep counting them. So here's my table. You'll note I have taken the natural numbers. We'll note 0 is not in here. Maybe that matters to us. You can always just throw in a 0. It doesn't really affect anything. And so I have a countably infinite number of natural numbers going along the top on the heading, and I have a countably infinite number of natural numbers going down the left side. Those are the row labels. And what I simply do is I take the row label and I divide it by the column label, and I get, for example, in the first row, 1, 1/2, 1/3, 1/4, and in the first column, 1, 2, 3, 4. There's a little bit of an annoying thing here. This diagonal is all ones. 2 occurs twice. 4 halves and 2 once are both the same, and then 1/2 occurs twice. 1 over 2 and 2 over 4 are the same. So sort of there's these lines coming out of 0, 0 that have the same values on them, right? And we see 2 of them. So how do we deal with that? We're going to build a set. We're going to build a set by ignoring duplicates. So one of the great things about not writing a closed form solution is you can just say, well, I'm gonna write out this table, and I'm gonna take things out of this table in some order. And because I'm writing a proof, I don't care how hard or tedious it is to say that this could happen. I simply say, if the number's already in the set, I just don't count it, right? I just skip over that number. So for example, if I say, hey, I'm going to take the first 3 elements from each set, or from each row, and I'm just not going to take duplicates. I say, all right, I take 1, 1/2, 1/3, 2, I just skip that. I just say I skip that. We agree I skip that. Of course, that's possible. You could write complex if statements, computable. Then I take 2/3, then I take 3 3/2. Oh, I'm just going to ignore that, right? And you continue in such a manner. And then we've already taken 2 as well, right? Okay. The one thing we have to look out for here is what you cannot do, and this is extremely against the rules, is you cannot say, I take all of the elements of the first row, then I take all the elements of the second row. Why can't you do that? Well, there's an infinite number of elements of this first row, which means how many elements do you have to take out of this set before you get to the second row? Well, infinitely many. So that's not a bijection, right? There is no natural number that corresponds to this index. The index of this thing is infinity plus 1. That's not a natural number, right? That doesn't make sense. So somehow we have to make sure that we get to every single value in some finite number of steps. And this is how we're going to do it. We're going to use a pairing function. What is a pairing function? Well, I just found this in a textbook somewhere. This is one example. And what does this do? Well, given a range for j in one range 5, right? What we're going to do is we're going to notice that we can get to coordinates, which are of the form I comma j, using nothing but a single numerical value. And how are we going to do this? Well, we take the pairing function, which takes the coordinates and returns a single individual number. So we're going to say we take 1, then 2, then 3, then 4, then 5, then 6. And in this way, we're going to sort of snake across our table. And then the only thing that remains to do is say, hey, you know what? We're not going to worry about those duplicates. So these things are all 1, and these open spaces correspond to what was there? If that's 4 over 2, so that's 2, right? And that's 1/2. Sorry to hear. And so we can say, hey, look, what I've done here is I've shown I can go from between pairs of natural numbers and single natural numbers. This thing is a bijection from n to n2. Those exist. Here's one right here. You can go the other way, of course, right? Then it's much harder to stop your rows at appropriate places, right? And in this manner, I show that, hey, oh, are you at position 3 by 4? Well, you are the 3, 4. 3 plus 4, that's 7 minus 2. 5 times 1 plus 3 plus 4, that's 6. Okay, 7 plus 6. 742 divided by 2, whatever, plus j. Ta-da, easy. And then we add the one appropriate caveat that you should subtract something for this for however many duplicates there were previously. So this is actually 5 because we don't count this 5. You can think of this as loading the fractions onto a stack, such as with a pushdown automata, and you just make sure you haven't already read something. It's pretty hard to do that with a pushdown automata because you're not allowed to read the stack, but you can do it with a Turing machine. Right? You can just write them on another tape. And every time you see a novel value, simply write it down on your list of rational numbers. No problem. So there's our proof. Let's show the diagonalization lemma quickly, and then we'll be done for today, and we'll come back next week for undecidability. Recall, collect our thoughts. We're showing that there's different sizes of infinity, and we're going to use this pretty soon to show there's things we can't decide with our Turing machines. You can probably guess where this is going. A clever student will guess where this is going, right? And if you haven't guessed yet, just keep reviewing the material. We will assume R is countable, and then we'll find a contradiction. No problem. Okay, so what's countable mean? That means that I can write down essentially a row or a column or a table or whatever you like. And I say, aha, I have written down every single real number, and every single real number corresponds to some natural number. We have an obvious problem here. 3.14159 is, let's see if I can say this out loud, 314,159 divided by 1 million. That is a member of the reals, and that is a member of the rationals, because that is a fraction. Pi is a transcendental number. It has no fractional form. It provably has no fractional form. The proof is out of scope of this class. Go take a number theory class. Pi is an element of the reals that is not an element of the rationals. Now, it is insufficient to show that there are elements of the reals that are not elements of the rationals, because 1/2 is an element of the rationals and not an element of the naturals, and there is a bijection there. But this pi is going to tell me something interesting, because I can use this pi for something. I can use elements like pi for something. There are, for example, an infinite number of multiples of pi, and there are an infinite number of transcendental numbers, right? So we're going to take all the real numbers in R. Take them any way you like. You can start with pi. You don't have to. And we're going to tease a little bit where we're going this, which is we're going to say one of the ways to express the real numbers, we can write them down. Now, we can't necessarily write them down on a finite amount of paper with a finite amount of ink, right? But they are the numbers for which there is some string representation, either in decimal or in binary or in any other number system. The number system does not matter, but they are expressible as strings. The only real thing that you need to be able to do is you need to be able to use a decimal point, right? Or perhaps not a decimal point, perhaps a hexadecimal point or a binary point. I have a strong preference for binary because I think it's easier to think about. Many of us have a strong preference for decimal because we grew up with that. Everyone has some opinion about hexadecimal as well, and there are other number systems, right? So I'm gonna begin creating my listing, and I'm going to use decimal numbers for n on the left-hand side, and then I'm going to say that I have some function that maps from the natural numbers to r. So perhaps you've been sitting here listening to me the whole time, and you think, well, Professor Calvin, it is ridiculous to claim there's no such correspondence between n and r. I have one right here. Look, I have successfully written down every natural number, and I have it corresponding to a real number. And I got every real number. I didn't miss a single one. You say, okay, no problem. Simply show that to me, and then I will believe you that there is a bijection. And of course, this is similar to the proof technique of proceeding by contradiction, right? So all we need is this table, right? We just have to fill out this table. It should be simple. So go ahead and think about how you would fill out this table. If you want, you can pause and come back. Here is an example of a table. Have some interesting values here, right? You may know what some or all of these are. But we start with pi, of course. For the math enthusiasts at home, note that I have one indexed to my list for you. Then we take e, take 0, take 1.414, which of course is square root of 2, take 1/7. Interested students may recognize z from somewhere. That's a little bit of a brain teaser there. And then v is equal to 1.2, 3, 4, 5, 6, 7, 8, 9, and perhaps we can imagine that after that 9 there's an a. You know, perhaps there's no law against these being hexadecimal representation as well. And so we simply take any given number. What number are you missing here? Well, I'm going to show that no matter what's written down on your table, there's a number you forgot. And I'm going to use your table to build that number. I'm going to start with your table, and I'm going to say, I suspect you're missing a number that starts with 4. And you say, oh, Professor Calvin, write down here, a table at position 8. I have a number that starts with 4. And I say, no problem. I'm going to keep adding to this 4. I'm going to say, well, you're missing a 4, 4.8. And you say, oh, yeah, it's true. My first value that starts with 4, but this is present a bit further in the table. No problem. I say, okay, no problem. I'm going to keep adding. I think you're missing something that is 4.81. And at this point, an astute student will note that 4 differs from this value in its first position. And 4.8 differs from this value in its second position. And 4.81 differs from this value in its third position. I make no claims that I disagree with all of the numbers in every position. But what I can do here is, because I can express a string that is of potentially infinite length, right? I can go all the way down this table, and I can disagree with the element in the table at any natural number position, because I have a digit in every single natural numbered position. So I can always disagree. 4.8159. More than that. More than that. We claimed there was probably going to be a 7 here, so we place an 8 there. But no matter, I've already shown with this whole table I can disagree. And there is no limit to how long I can keep adding digits to the end of this thing that disagree with your table. So that's the diagonalization proof. Interested students will note that this means that I'm missing a bar here, that the cardinality of r is equal to the cardinality of n. And sometimes it is expressed this way. And the reason for that is that you have a natural number. It's the same notion as the deterministic versus non-deterministic automata. You need a way to express the inclusion or exclusion of every single natural number. There is one real number for every set of natural numbers, because the digits represent a set of natural numbers, or perhaps a sequence, right? And with that, we have concluded diagonalization. Well done, good job. Look up contrast diagonalization if you don't understand it. This is one of the topics in the computability class that I think everyone teaches, everyone knows. When I was teaching my theory of computing class, I didn't I was not instructing diagonalization. They say we use a diagonalization here, and it was assumed you already could do it. And they could do that because they were in one department and everyone knew what everyone taught, right? So in the first course of a master's program, that's inappropriate. I don't know if you've seen diagonalization, and I shouldn't assume you've seen diagonalization, so I'm going to teach you diagonalization. But what this does mean is that it is uncommon for someone such as myself to teach diagonalization frequently. This is taught by a theoretical mathematician who is accustomed to teaching topics at this level of difficulty and in this manner of rigor, such that later proofs can rely on it, right? And so sort of all of the topics this term, this is the most purely mathematical concept. This is the most purely mathematical lecture. There could be other mathematical lectures in a theory of computation class, and we may do some of them depending on time. The motivation of all of this is to suggest that if you do not understand what I'm saying with diagonalization, look it up. There are many people that understand diagonalization quite well and are experienced explaining it to people at a variety of backgrounds and skill levels and familiarity with mathematics and familiarity with computer science, right? I have introduced what I hope to you to be enough terms, and I have talked about things in the manner that I would instruct them to a computer scientist. My emphasis on use of the terms surjection and injection, my emphasis on using sort of this like type hinting notation to refer to my functions. These are the little bits of flair that I bring as a computer scientist, right? But mathematicians use all of these things as well. They simply emphasize them differently. And there's no real difference at this stage in between computer science and mathematics, right? Like, we don't want to be dividing up fields where there's no benefit to do so. In 1891, there was no difference. Perhaps there is still no difference now. So, as you're thinking about this, the way you should look forward to undecidability is I did one very sneaky thing. And I showed that there are more strings than there are numbers. This is a bit of a problem for us, right? Been kind of treating these as the ability to go back and forth between the numerical representation of a string and, the ability to talk about a binary number as storing potentially any value. Can I write down every digit of pi with a Turing machine? We've also been storing computers as strings. And we haven't really specified if all of these computers we can store as strings, how big we need the alphabets to be, and how many tapes we need to store them on, right? And then we've also been writing computers that study strings. And, okay, so this means it's strings all the way down, right? And we just treated strings as being much more similar to R than to N, which means we might be dealing with things that look an awful lot like the real numbers. And the real numbers are not so well behaved as the natural numbers. And so this thing is going to be undecidable. And I'm sorry it's going to be undecidable. I hoped it was decidable too. But we'd all be out of jobs, right? It would be a little bit too easy to do computer science if this thing were decidable. So that's what we're getting to. That's what's coming for next week. I've posted the first problem set. I've posted as a collab document, which means it's a .ipymb, which means it can be converted freely into Quarto Markdown, and it can be hosted in a variety of manners. It's easy to render as HTML. And that is on finite automata and regular languages, and that'll give you a little bit of practice actually working with these things and keeping clear in your mind the differences between all of them. And it is good to work on that as we build up to doing those same operations with Turing machines. So thank you. This has been the second week, or week 2, right? It's hard to know what week 0 and week 1 are, but we're back from residency. It's an asynchronous lecture, and this is the first lecture that has a corresponding problem set.